Yeah, good afternoon to you all. I'm Kapil Oberai. I'm the faculty of Geoinformatics department at IIRS. Welcome to this session on overview of big data analytics. So in this session, we'll cover a basic overview on the big data and the various aspects. So we'll start with the brief history of data, how the data has evolved, what makes a data as a big data, as the data was always of a higher order. We'll also define the big data and the various characteristics, primarily defined by the various V's. The various types of data type that we can encounter in the big data. Structured data we are primarily aware of, where the data is organized, have a related structure, but big data, apart from this handling the structured data, it also have a data type like semi-structure, or sometimes there is no structure to the data. Maybe the data coming from, let's say, the social media. Next, we'll also discuss the how does this big data concept fit into our geospatial domain, and what are the challenges specific to that. Now, in order to handle the big data, so the traditional mechanism will not be working, so we'll have to work on the distributed and the cluster based environment, and there are some specific tools that are available for handling such big data. Two of the popular tools are Hadoop and the Spark. We'll cover those basics, and then finally I will talk about the cloud computing and the and how does it helps in addressing the big data challenges. Now, a brief on the history of the data. So primarily with the coming of the computer somewhere in mid 1970s, uh, from the paper based systems we moved to the digital system, where there's a huge volume of data being generated and also converted from analog to the digital form. But what really makes a difference was the coming of the internet somewhere in 1990s, which really led to the explosion of the amount of information that the user can maybe consume and also generate, which led to the huge enormous explosion of the amount of data that we are now seeing in the current days. And simultaneously, there was also advances in the computing and technology. The cost of the hardware also come down relatively, and the users are also collecting and storing large amount of data with high level of efficiency. With the penetration of the internet, the availability of the smartphones, and also the broadband connections, and also the reduction in the price of, let's say, the broadband connectivity, has led to the wide uh, wide exchange of information at a global scale. Internet being a mechanism through which the people can exchange their ideas, exchange information. So one person sitting at one place on the earth can communicate with the person at the other corner of the world. And also with the coming of like social media, the the connected devices, maybe smartphone, the various kind of IoT sensors which can monitor the health, the environment, and other things, the availability of the broadband connection, and also penetration of the internet and the broadband connectivity at the grassroots levels has led to the huge voluminous amount of data that is being generated. Other thing is, from we have also moved from web 1.0 to 2.0, in the sense that we were more like a consumer of the data, but now with the coming of the social media, the user participation, the citizens or the users are also generating a huge amount of data that is very very valuable if you want to make some informed decisions. This is small infographic depicting how does the form factor have maybe miniaturized, and also how does the more storage are nowadays available. For example, in 2005 we are able to store roughly 128 MB, but now we can maybe store more than 128 GB on a small microchip. And also the cost of these hardware, let's say, have also reduced, so it is mostly within the reach of the people, and so people are also consuming, collecting, and maybe contributing to the whole data ecosystem. So currently we know in the form of a data deluge era, so huge amount of data is being generated from terabytes to petabyte to the zettabytes, And then just to give you a feel of the amount of data that is being captured, this infographic on the left depicts the amount of data that is being generated every minute. This is from this domo.com, if you can refer to that website. So just this infographic depicts the quantum or the amount of data that is being generated from 231 millions email sent every 1 minute of the day, to the amount of text messages or the number of people who do a Google search or the Facebook share, the number of people who send messages through Twitter, or the number of videos as the users upload. So if you see, these are the huge numbers of data, and these are all internet based companies who want to use this data to make an informed decision, because nowadays data is a new oil. So we need to find it, extract it, refine it, so that we are able to generate the revenue and use it as the best possible mechanism, so that we are able to serve our end user or customers in a better way. So now it boils down primarily to handle this data and to make the data driven decisions, which is very very crucial to any business. For example, every click on a particular internet facing website can tell you maybe what kind of user are interested in what feature, so that we can customize and tune those features to that, to his or her needs. The classic example is a recommendation system that you can find across in various such sites. Other thing is the global internet population growth has also increased. So from 2016 roughly around 3.4 billions to now it is 5 billion. So the as per this infographic again from the, it says that as of April 2022 the internet reaches 63% of the world population. So you can see that the whole world is now become a village, and they are connected and they are able to exchange the data across, and over 93% were our social media users. So you can see that how much the people are making use of this data, generating data. And as I said, most of these data could also be geotag, which is also from our geospatial domain, could be very useful, and people have started making use of this data in an amicable way, so that they can make best use of the data, increase their business, and also serve their end users in a big concept. Just to give you a number feel of the numbers, so in our school days we used to heard about the bit 0 and 1, to nibble 4 bits, to byte 8 bits, but nowadays we are talking about zettabytes and yottabytes. So zettabytes is roughly 10 raised to the power 21. You can see the number of zeros after the 1. So we are talking about the huge number or the amount of data that is being captured. So the huge amount of data is being captured, and so there are various causes, primarily because of the availability of the, let's say, the internet, the within reach, and the grassroots level access of the broadband connectivity, and the people not from the consumer are also developing and generating the data sets that could be various advantages for the businesses as well as for the users perspective. Now let's also now define what we mean by big data. So when we talk about big data, we are not talking primarily from the volume perspective, but it is from talking the concept that the data of myriad data sets, which is somehow difficult to process using the traditional data processing platforms. Let's say a typical database based approach, or the state of the art approaches for data processing. Another definition could be that big data is a term for a collection of data sets that is both large, so we are talking about volume, and also complex. So it also have some complexity in terms of difficulty to be processing using the on the hand, let's say, database management tool or traditional data processing application. So handling this large volume and this complex data of, let's say, structured, semi-structured, unstructured, maybe is very difficult to handle using the traditional data storage or retrieval mechanism or data processing techniques. So we require some different tools and approaches, maybe from standalone to a distributed to a cluster based approach, and also from serial to a parallel. Instead of batch based, we could also need to do some stream processing to make sense of those data. So big data, as I said, is a term that we use for the collection of data set that is both large and also complex, and somehow it becomes difficult to use using our traditional method. So this is the definition that we have got, but other characteristics that define big data is somehow represented by various V's. So every time you come across a big data, you will find out these characteristics defined in terms of various V's. So started with the 3V, we talk about the volume, which is the size, and also the velocity, which is the speed, and variety is the different types of data that are being generated. So as you can see from this infographic on the right, so the moment we talk about volume, we're talking about the size ranging from terabytes to zettabytes and yottabytes, let's say. The moment we talk about velocity, we're talking about the speed of generation of the data, and also which leads to the processing of data from batch processing to almost real time and then stream processing. And the third is a variety, which is the different types of data that is being captured or generated. One is a structured, and then some could be semi-structured, which have a way of both structured and unstructured data. And similarly, some could be pure text-based or unstructured data, which you can't somehow fit it into your typical database management systems. Subsequently, the V's were also enhanced to incorporate the other aspect, which is the veracity, which talks about the untrustworthiness or how much the data could be trusted. And now this 5 V's is primarily a standard when we try to define big data and what are the various characteristics. So we talk about the volume, the velocity, the variety, the uncertainty or trustworthiness of data, and the important thing is the value. How could we make best use of the data so that it's serve the end users and also the business for which who is primarily collecting this data. So the big data primarily is now defined by this various V's ranging from 3V to the 5V, talking about not only the big, when we say it, not only from the volume perspective, but also the complexity is increased the moment we add the speed of the data and also the different types of data. Because if we are well aware and know how to handle a structured data, because we can put them under a schema and then we can retrieve based on the, let's say, the query languages, or you can use different programming languages. But the moment we are dealing with the different types of data, some are structured, some are unstructured, and some are in the in between, like a semi structure, then it becomes a difficult to store them, process them, and maybe analyze at one go. Which also bring us to the challenges about how can we capture now these different types of data. So we have, one is the pure volume, the sheer let's say the size of the data that is coming, but other is at the speed that which it is coming. See, batch is something we are well accustomed to. Maybe at the end of the month we can generate reports, but now as and when the data is coming, we need to process it, store it, and also provide some analytics on that data. So the challenges are also now with reference to how we can capture them, also how we can store them. Similarly, once we have stored, can we retrieve them and also transfer them to one place to another, because transferring this data of also diverse data is also a challenge. And then finally, once we have stored them, can we now able to analyze these varied data sets. Now visualization itself is a huge challenge in the sense how we can visualize a terabytes of data over a web which is being transmitted. So again, there are various challenges once we talk about this big data, not from purely from the storage part, but also from the analysis and also from the other aspects. Now let's also briefly discuss what we mean by the structured, semi-structured, and the unstructured data. So structured data, as the name suggests, the data has a predefined structure, or in the database perspective, we can say that they have a fixed schema, and somehow we know that what are the various columns, which columns contain what values. A good example could be the data in a, let's say, Excel or a comma separated CSV file, where we know that one field is separated by a comma or a semicolon or a tab. And then these kind of let's say delimited file, we are able to make sense of it, because if these comma separated values are there, and then we are storing, let's say, the name of a place, the location, and other things. So we primarily have an idea that first column contain the name, and second and third column, let's say, contain the longitude and the latitude kind of an information, followed by other attributes. But once it comes to unstructured, where the data does not confine to a fixed organization schema, and it is arbitrary because people can put any kind of information into them. Classic example could be the data from the social media, like the post on the Twitter or the messages that we exchange over a Facebook. And then some of these data could also be geotagged, but it purely comes under the unstructured, because whatever the user are posting could be a message, it could be an image, it could be emoji, it could be various other kinds of information that the user is putting, and somehow we are not able to in a simple way maybe able to put them into a columnar structure which we are very accustomed to when we talk from the database perspective. The third types of data is a semi-structure, which is in between the, let's say, the structured and the, uh, the structured and the unstructured. So as the name suggests, it's referred to data that has some elements of structure and some aspects that somehow is arbitrary, which can't confine to any form of structure. A good analogy example could be our personal phone diary, where we could have columns for name, address, phone number, and then a column where we write some freehand notes. So the name, address, phone number will confine to a type of data that we can put, but notes could be your could be any, it could be scribbling kind of a text, we can put some images, we can put some figures and those things, so it confined primarily to a semi structure. So have a some structured component and also the some free or a arbitrary component which does not fit into the structure. Now from our computing perspective, the common example is a JSON and XML kind of a format, which for example, if I talk about JSON, it generally use key and value pair, and then it contains, encapsulates primarily the structured as well as the schemaless or the arbitrary kind of information within this single, let's say, a JSON object or a document. Another example could be our email messages that we exchange, which have a structured part in the sense that the name of the sender, the time when it was sent is common to all the email messages, but the main body where the user write the content of the mail that you want to communicate could be unstructured in the sense, again, people can put table, put images, put HTML elements and various other kinds of content into those topics. So it is difficult to understand maybe what kind of information that we are portraying. So we have discussed so far the how the data is evolved from the from the analog to the digital with the coming of the internet, the penetration of the smartphone and availability with the broadband access, the user primarily from the consumer of data to the generation of data, the various these internet kind of based companies which are also generating data has all led to this vast amount of data that's being captured. And then big data we primarily define in terms of the various V's from velocity, volume, variety, veracity, and also the value aspect. And now we have also discussed what we mean by structured, semi-structured, and the unstructured data. So structured data by far now is very easy to understand, but these kind of unstructured and semi-structured data, which are primarily a major type of data that is being generated. You talk about IoTs or you talk about the social media feeds are primarily fit into these categories. So how we can make sense of this data is also a challenge. Now, if I discuss about the typical analytical workflow for a big data, so the data is captured from various sources. It could be from a traditional database management systems. It could be the data warehouses wherein the data is being captured, maybe the subject oriented time invariant data is being stored, and the data could also be accessed over an API through other organizations, or data could be streamed in through the social media feeds, or also from the, let's say, the IoTs that we have installed. So from the data sources, now the next thing is once we have captured the data is coming in a free flowing manner, we need to store and manage them. And then the management approach start with the pre-processing of the data, initially cleaning of the data, and sometimes we also need to aggregate the data in order to make sense and also for use it for the further processing. Sometimes we also need to perform those transformation, and typically in a data warehouse we use the term like ETL or the extract, transform and load kind of a concept for transforming from one format to another, and all those pre-processing tasks has to be done before the data could be used for the further processing. Once the data is from various sources is coming to our system, and then we have done the necessary checking, cleaning, filtering, aggregation, the data next part is the modeling part, where depending on the requirement various models could be decided and then suitable can be picked, followed by the training and the testing of the data based on the existing collected data, and finally once the new data has come, the model could be applied of the data, and then classification and regression kind of an output could be generated, and finally the results and the visualization stage, where how we can get insight from the data or the hidden information from data mining to machine learning techniques could be utilized to basically to have an interpretation, prediction, and also the visualization of the data sets. Now if we talk from the category of analytics, so primarily we can define them as either descriptive, predictive, and also the prescriptive. Descriptive primarily tells us what has happened in the past, so it is primarily used for modeling the past behavior, and from the existing data we are able to tell why something has happened. The next part, the next higher level will be the predictive, which is wherein we are able to forecast the data based on the existing data set. So this part is the predictive. Third, which is very important, is called the prescriptive, which wherein it can assist the decision making. It is like from the user's perspective, given a scenario what we should do now. So from descriptive, modeling the past behavior, to forecast, to assisting the user in decision making. So these are the various kinds of analytics that the user needs to perform depending on the requirement. So the typical workflow looks, as I said, from the various sources of data that is coming. So you can see the volume, the various variety of data sources that are involved, and also the speed of which it is coming. The data has to be cleaned, aggregated, transformed, so that we are able to integrate it, and somehow the modeling techniques is used to make sense of the data, and finally the data is interpreted for use for a particular purposes. Now, from the big data analytic perspective, we can also define or categorize them either as a text analytics or audio, video, and also the social media or the predictive analytics. So text analytics, as the name suggests, it is primarily used for extracting information from our unstructured text. So it is like extracting meaning from the blogs, the survey responses, and also the social media feed. So our natural language processing kind of a analytics comes primarily under the text-based analytics. Next is the audio analytics, wherein refer to analyzing and extracting information from the audio data, and this is primarily used in the customer call centers, and maybe also in the healthcare companies when they want to serve the end users. The third type is a video analytics, and as the name suggests, here we are more into analyzing, extracting meaningful information from the video streams. That could be maybe static camera feeds, or it could also be the real or the real-time camera feeds that are coming. And this is quite useful in the video surveillance, and people are also nowadays also using it for, let's say, traffic monitoring and other kinds of information domains. Now social media analytics is a very big area, where the people are also trying to analyze the data that from various social media platforms. It could be Twitter or Facebook and others, because it also gives us sense of the what the people are feeling on the ground. And if you see that people also come to social media and also share their views, so it is a good, let's say, a reference point for making sense of what the people are thinking about their product or services on the ground. So this is a whole sector in itself, where people are also using this let's say social media instead of maybe you're doing a, let's say, a good ground based manual survey for understanding about the product requirement and other things. So in the literature you will come across that people have used social media like Twitter and other things for analyzing the traffic, for, let's say, the weather, even for the disaster management. There are huge kind of case studies where the because and in the case of disaster, such kind of media platforms become very important to identify the people in distress. So this is a whole area where the people have make use of this big data for understanding and also gathering the data and using for various domains. Now predictive analytics is the one that people are frequently using, for predicting the future based on the past and the current data, and then various machine learning and deep learning algorithms like decision tree, linear logistic regressions are prime examples of this predictive based analytics. Now, if I talk about the big data process, we have discussed the analytical workflow. So we can have two, let's say, the steps. The first is the data management step, from the acquisition and recording to extraction and cleaning and the annotation of the data. So this is where the major, let's say, effort is being put to how we can get the actual data that we can use for model training or making sense. The other aspect is also the integration and the aggregation and also the transformation of the data, because the varied data has to be integrated before it could be make sense of. So once the data is acquired and managed, the next part important where we should put our emphasis in getting the insight from the data. This is where the modeling and the analysis approaches that we talk about comes into the picture, followed by the interpretation of the data and making it useful to our end use. Now, from the geospatial perspective, geospatial data was always a big data, in the sense we are always working on large volumes of data. But now we can think that there are various kinds of satellites that are collecting data. There are ground data that are also there. Data also coming from IoT devices. The social media, which are geotag feeds, are also very useful. So from the geospatial big data, we typically refer to the data sets that exceed the capacity of the current computing system. And this is a figure, however, quite old, but it says that in Google about 25 petabytes of data is being generated, and most of it is spatial temporal data. And then we also know that these spatial data are very valuable for the governance, for decision making, and also the situation on the ground. The infographic that you can see on the below here is depicting the Millennium Development Goals. These were precursor to the and now being replaced by the Sustainable Development Goal. But just to a glimpse of the picture, that there was 15 of such Millennium Goals, and the one in the encircled by a rectangle are the one where the geospatial data is of the huge importance, right from the sustainable development and climate change studies to clean water, population resources to health issue. And we have seen during the COVID times how this data sets are quite useful, and where people have generated or captured data from the social media feeds and also from the ground based information, and try to identify people interested and to serve them to your end use. Also from the apps like Arogya Setu, a lot of data was being also be people also maybe downloaded those apps to know about the COVID situation. Similarly, peace and conflict, energy resources are various sectors where the huge volume of geospatial data will be very useful. Another trend, as you are seeing, especially in India, is the internet traffic from mobile devices has exceeded from the desktop computers. So nowadays there are a lot of mobile internet devices, so the people are also consuming data as and when they are moving around, and also contributing to this data deluge era. Now, just to talk about the various big data sources. So primarily what we have discussed is the earth observation or the remote sensing data is a major player, huge, because there are various satellites that are being launched and being used by various nations, India being also one of them. And then also there are some legacy data, and also the surveying and mapping data is also being done by the various national mapping agencies, and with the opening of the data policies, so which has also led to the huge volume of data being generated. Third and fourth are the location based data, and also the data that is being generated through the social network. As I said, some of the data sets are also being geotagged and has been used for various scenarios. And then what has also led is the penetration of the internet, and also the, let's say, 5G connectivity that are available. So there are a lot of connected devices that are linked to the internet, called as the Internet of Things, which are also generating the huge voluminous data every second. This could be monitoring of the pollution, maybe the temperature. It could be from the healthcare perspective, your smartwatches and all are generating a lot of amount of data. Just to give you a glimpse of the data volume that we are talking about, so this slides talk about the data set generated from various Earth observation program from Landsat to the Sentinel. As you can see from the 2014 and 15, it was less than 1 petabytes, and now combinedly in roughly in 2019, it is exceeding more than the 4 petabytes. So these are the voluminous data that is being generated. So this is only from the, let's say, the USA and also from the European agency, but also our Indian satellites are also generating huge amount of data. So maintaining this data, keeping it for a long-term perspective is also a requirement from the data providing agencies. But if you are working on a long-term project like climate change, energy and so on, you also required to store and manage these data. So these kind of aspects also has to kept into mind, so that such data could be best used in various scenarios. Now, talking about this big data, so one thing is to handle this voluminous and variety of data. Maybe the traditional approach of storing them in a typical RDBMS system may not be the way to go it. And then from the big data analytical framework perspective, there are two popular framework. One is called as a Hadoop and other is called as an Spark. We'll see one by one. First, let's talk about the Hadoop framework. So Hadoop is a software framework and is an open source which allows us to store and process this big data on a clusters of commodity computers. So it does not require a high-end kind of a systems to build those clusters or a group of systems that are working together as one. Now Hadoop primarily has two components. The first is called as the HDFS, which stands for Hadoop Distributed File System, and second is the programming paradigm called as the MapReduce. So the first component, HDFS or a Hadoop Distributed File System, is the storage or the fault tolerant storage part of the Hadoop, and is a distributed file systems that run on the large clusters, and it provides high throughput access to the underlying data. The important thing is it can store both structured as well as the unstructured data. And since it is a distributed file system, it divides a large files among various nodes or machine in a cluster, and then it is able to provide a high throughput data access. The other thing is it is also enables the fault tolerance, which means the file is divided into different blocks, and then the blocks are stored across the clusters, so there is a redundancy also kept into mind. So by default there is a replication factor of 3. However, you can increase it if you wish, but every block may be stored at least 3 in the various nodes of the cluster. So as you can see from this infographic here, which demonstrate the fault tolerance in a HDFS based system. So the file, let's say we have a file which is divided into 3 blocks, and then this D1, D2, D3, D4 are our nodes of the cluster. So you can see that the various blocks are replicated across various nodes, and hence it is able to provide a fault tolerance in the sense that if suppose the nodes come down, let's say D1 node is down, still the data is being able to access from D2 and let's say the other D4 nodes. So hence this Hadoop distributed file system takes care of handling this huge amount of data, and also allow us to have this fault tolerance, because we don't want our system to stop working once, as a one node of the cluster will go down. So hence it allows the fault tolerance in case this one of the nodes goes down, the data will be replicated, and hence our process can continue working. And which also talks about the scalability of the cluster here. So we can add more nodes as and when we require them, depending on the complexity of the data and the application that we are working. So the second component is the MapReduce, which is primarily a programming framework. So first is about the storage part. The second is about the programming framework to make sense of this data in a cluster environment. So again, the MapReduce is a programming component which takes a large task, and as the name suggests, divides them into two phases. One is the map part and second is the reduce. So as you can see from this name, MapReduce, so there are two phases to this part. One is a map and second is the reduce. So in the first part, the map phase, what primarily happening is we are trying to do a divide and a conquer kind of an solution to the large data here. So in the map phase, we divide the large task into smaller pieces, and with the each small piece is given to one active node in the cluster which work on that task, and the output of those tasks are again combined by the another phase called a reduce phase, so as to generate the final output. So as you can see from the figure here, the large data is divided into small chunks of data which is given to each nodes, which is in this case is known as the map phase, which works on the data, generate the intermediate results, and those intermediate results are again combined together to generate the final result. And this is maybe the scalable way of working on large data, where the problem could be divided into smaller pieces of the data, and because of the data locality issue, the process is running where the data is there. It makes the system works very fast. So the programming paradigm consists of a simple concept of the mapping, dividing the task into smaller pieces, and then giving them a smaller task to each, which is running on each and every node. The intermediate results are being combined by the reduce phase to generate the final output. And we could also understand by this raster-based map reduce processing example, where the large raster file, let's say we want to process the DEM data, which can't fit into our memory system. So what we can do is we can divide them into different tiles of data, could be stored in a fault tolerant manner in a Hadoop cluster. In this case, there are 6 nodes, and then the work of processing the data could be work on tile by tile, which could run on the various data nodes, and the output is finally combined to generate the output DEM product. So the large problem could be divided and then work on a tile by tile basis, depending on this and the number of nodes and the data size, and where each node performs a part of the task. It could be local operation that somebody is doing, maybe enhancing data or some other classification task could be there. Here we are talking about the processing of the DEM, and the output is generated, which could also be returned back to the HDFS system and could be used for the further task. So this is a good way of dividing and conquering of a large problem into smaller tasks, where each task runs across the cluster, handling a portion of the task, running simultaneously. In case the one of the node goes down and there are issues, the other nodes are also there to handle it, and we are able to complete this large problem task in a efficient manner. Now Hadoop does not has other components, so generally it is called as an ecosystem of the tool. So apart from the storage and the replication, which is the HDFS system, we also have a programming paradigm, as we discussed now, as a map reduce. But there's a whole ecosystem, a bunch of tools that work together in order to solve the various problems. For example, if we are looking, in a cluster environment, the cluster resources has to be managed. So that is being done somewhere by the yarn kind of an utility. Similarly, if you want to perform a warehouse kind of an task, then Hive is one of those components of which fits into this Hadoop ecosystem, and which gives you SQL kind of functionality for working on the large, let's say, warehouse environment. Similarly, if you want to work on scripting environment, this provide a piglating kind of a language where we can write a scripting language for processing the data. Similarly, if you are looking for a machine learning, then there is a library called Mahout, and then if you are looking for let's say the understanding or processing of the stream data, this Kafka based messaging and data integration is one such tool. So apart from the underlying HDFS and the MapReduce framework, there are a whole bunch of ecosystem tools that you can use, right, from machine learning to maybe Hive for a, let's say, warehouse or a batch processing, and also for, let's say, if you want to bring the data from other system RDBMS to the Hadoop system, we have a Scoop kind of tools. Similarly, Zookeeper for coordination, and then other kinds of tools like Ambari for management, which is a graphical user interface for managing your whole Hadoop ecosystem. If you want, we can also include HBase or this NoSQL kind of a system, which also provide a columnar based approach for fast read and write. access. So depending on the requirement, various ecosystems or various tools could be integrated to get the desired job. The second type of framework that we'll encounter under the big data is called as a Spark. Now, compared to your Hadoop based framework, the Spark is primarily an in-memory computing framework, which means it is with the reference to the Hadoop, it will be much faster because it is able to compute, perform those tasks in the memory itself. And it make use of a structure called as RDD, which is stand for Resilient Distributed Data Sets, and is primarily in-memory data store where the data is resides in the memory. However, it could also be later stored to the disk. Now, compared to the Hadoop, Spark is much faster than the Hadoop because it is an in-memory computing framework. Unlike Hadoop, where every read and write has to be the disk, so for every map task, it will read from the disk, and intermediate steps will again return to the disk, and the reduced part will again read from the disk and write to the disk. So as we know that IO cost is more compared, and the memory in memory processing are always faster, hence Hadoop is pretty slow compared to the Spark. Hence Hadoop is primarily used for batch based kind of an task. Now other advantage of Spark is that it also enables to perform iterative tasks, which is primarily what we do in a spatial analysis, because we perform a series of steps and then we want to replicate it again. Other good thing about this Spark based framework is unlike in a Hadoop ecosystem, as I said, for different kinds of let's say the activities that you want to perform, there are different bunch of tools that you need to enable or maybe append it to your Hadoop ecosystem. However, Spark is called as a unified computation platform, in case it handles most of those kind of a use cases. So if you can look on the infographic here, so the Spark does not require let's say Hadoop or a HDFS kind of a system. It can use any of the data sources, and the primary construct is the Spark core, followed by it has the support for Spark streaming, so you can handle the streaming data. It also support machine learning and also graphic processing, and on the top it also support the handling of the structured data using the Spark SQL. Hence it is called as a unified kind of a computation for handling the big data. So in a single, let's say the framework, all the various types of activities, right from handling structured data through somebody maybe not familiar with the programming can use an SQL approach. For handling a streaming task, Spark streaming could be used. For machine learning, again the library is there, all the built-in libraries, various algorithms are built in, and also for the graph processing. And hence it is also called as a good for the real-time spatial analytics. And on the top of that, unlike a Hadoop where we are primarily writing in Java, the Spark allows us multiple programming language support. That could be Python, R, Scala, and another languages are also supported. And as I said, if you are familiar with the SQL, you can also go with the Spark SQL also. Now these frameworks are primarily for this big data perspective, but there are also customized let's say solutions also targeting the spatial data that we'll see in the subsequent slide. But from in the big data, when you come across, you will also come across these terms or like a NoSQL systems. Now these are also the kind of underlying storage engines for storing this big data. Now let's try to understand what we mean by the NoSQL. So the term NoSQL does not mean that they don't support SQL, which is a structured query language, but they means that they do not confine to a typical relational structure. So so they are the class of database system that offers an alternate solution to the relational model that we are aware of. So relational model, primarily the data is organized in the form of tables or rows and columns, and then there is a linkage between the various relations through the concept of the keys. However, relation database primarily have a need to have a schema in place before we can perform on any operation, whereas NoSQL systems are primarily work on the principle of scalability and performance, and they allow handling of the diverse data sets. And the advantage is that they are primarily the schema on read kind of a privilege they provide, so they don't require the data to have a predefined structure before we can work on the data. The four types of NoSQL database are columnar, graph, and also the key value pair, and also the document. So as you can see that the wide columnar data, if our data is primarily in a columnar format, we can go about in reading it, because it is much easier and faster to read all the data at one go from by reading from the single column, instead of worrying about a relation database or joining multiple tables to retrieve the data. Sometimes our data may be in some key value pairs, or it is in a typical document format. Then we can't generally put them into our relation system. So these NoSQL systems provide an alternate solution to the relational model, and they are primarily from the ground up built for scalability. Now the typical problem that we'll come across in a relational database system, apart from enforcing the schema, they are primarily vertical scalable, which means to enhance the performance, what we need to do is we need to buy a high-end server, increase the RAM, increase the CPU, add the more storage, whereas this NoSQL system from the ground up are made to be horizontally scalable. So, and they work on the commodity hardware. So they don't require that expensive hardware cost to go about in maybe pre-hand to before starting to work on those systems. So as and when our requirement is, we can scale up and scale down the systems. Whereas in a typical RDBMS based system, it is a vertical scaling, and there's a limit to how much you can scale a typical let's say a server, because there is a limit of how much RAM and CPU can go on board. So or otherwise you buy some more high-end machine. And compared to this, the NoSQL system, which are primarily developed for a cluster environment, and they are horizontally scalable, and also they allow flexibility in the way of storage of the data by offering different data models, which is not typical to the relational model that we are used to. Now the other thing is that the Hadoop based solutions, they are also targeted specifically for the spatial data. One of them is the spatial Hadoop, which allows us to analyze the spatial data using the capabilities of the Apache Hadoop, and it provides support for various spatial data types. Even indexing and various kinds of operations could be done. So if you go to this website that I mentioned, you can find a good tutorial, and also the single node virtual machines are also available, and then you can also work across through them. And there is also one more ESRI tools for Hadoop are also called as from the Hive perspective. You can also use for understanding and analyzing the data, and you can also connect it to your let's say ArcGIS kinds of environment also. Now from the Spark perspective, there is a tool known as the GeoTrellis, which is a Scala library that you work on the Apache Spark framework, but is targeted towards the raster data. So if you go to this geotrellis.io, you can know more about this library, which is primarily targeted towards handling the raster data. Now one more thing that we should also discuss here when we talk about analyzing the big data and getting insight from the data is that maybe the let's say typical organization may not be able to afford it to have those infrastructure cost in place or this cluster setup to be done. This is where this cloud computing comes into the picture, which is primarily a model enabling ubiquitous, convenient, on-demand network access from a shared pool of resources. That could be network, server, storage, application, and also the services that could be scale up or scale down, and also could be provisioned as and when the need arises. To understand what we mean by cloud computing, we can think in terms of utility as a service, or you pay only for the amount of time that you are using your services, like electricity in our homes. Now to give you a glimpse of the, let's say, the overhead of the cost that involved in setting up the infrastructure is that if you go about configuring a server inside your premises, then you have to manage the entire things, right from the storage, the network, to the CPUs, and on the top you will install the operating system and runtime before you can use it for processing or performing every operations. However, cloud computing provides service models that is called as an infrastructure as a service. So you can also, let's say, kind of lend the hardware resources from those cloud service providers and then use them for building your application on top of the infrastructure, which could be your network, storage, and the processor. So you can go to the cloud computing platform, which could be Amazon, could be Google Cloud Platform, and then you can, based on the requirement, you can provision the virtual machine or the bare metal machine, and then you can use it for the amount of time that you want to use. And that will be appearing more like your local machine because you will be accessing from the browser. That is something we call as a broad network access. And then the other characteristics of cloud is it allows on-demand self-service. So suppose today you required only a 2-node cluster, so then you can only provision them, and tomorrow your requirement increase. So on a real-time basis, you can enhance or increase the number of nodes, and you can only pay for the amount of time you are using. The second type of model is a platform as a service, where the vendor or the cloud provider gives you both the let's say the underlying infrastructure along with the runtime libraries that, let's say, Hadoop configured or Spark configured, and then that you can use for developing your application. So now you can think in terms of the time, cost, and the saving or the kinds of responsibility the individual has while maintaining of those platforms and also the underlying infrastructure. So you can see that from a small startup perspective, instead of spending time on configuring hardware, installing your libraries, making the necessary softwares working condition running, what you can do is you can maybe use the cloud-based services, and you focus more of your time on the actual part, which is the generating applications and serving your end users. The third type of service is called as software as a service, and this typical example is your email or CRM and word processing kind of services that you can get from the, let's say, the Microsoft, wherein the vendor manages everything from the storage, the underlying software operating system, and also let's say the software. You are looking for email services or FTP services or some other kind of service, and you only pay for the amount of time that you are using. So this is like a subscription based model where people can, depending on the requirement, they can avail those subscription based services, and the vendor takes care of all the storage, the operating system, updation of the softwares, the libraries, and then you only are using it through your web browser or either on your mobile phone or other kinds of apps. And then you don't need to bother about the underlying application. You are primarily using it as a service and paying for the amount of time that you are using. So again, coming back to the characteristics, so cloud computing provide on-demand self-service. So you don't require let's say a network engineer to configure or provision them from you. They provide a good user interface through which all could be done by the user itself. Broad network access, you can access it from the mobile or also from the desktops, and you can think in terms of that you are pooling the resources from the cloud providers, and then you can scale it up and scale it down as per your requirement, and it also provide a major service, so you are only paid for the amount of time that you are using. So you can think in terms of the, instead of first, if you want to host a website, first you need to on premises, you have to make sure the necessary hardware infrastructure is in place, make sure the operating system runtime libraries are in place before you can start developing an application and serving your end users. So in that way you can, and then also down the line somebody has to maintain it, upgrade it, and then keep safe it from vulnerability, security, and other consideration. So in that perspective, cloud computing provide a good alternative model to the on-premises kind of infrastructure. And from the big data perspective, now you can think that because we are handling such vast amount and diverse amount of data, it is very difficult for an individual to make sure that this infrastructure are available within an organization. So hence they can leverage these resources of a cloud provider, and then they can pay for the amount of time they are using. So the big data can make use of this cloud computing infrastructure for storing the distributed data on the cloud rather than on the local storage, and then they pay as a metered service for, and also the on-demand access as and when they the need be for the users. And nowadays, from the geospatial perspective, there are various cloud-based platforms that are available. A good example is from the Google Earth Engine. There is also one from the Microsoft and other companies. So Google Earth Engine is a platform for scientific analysis where you can get all the geospatial data already ingested into the system. So compared to your traditional way of working on a typical GIS project where you first download the data, pre-process it before you can use it for an analysis, here the data is already ingested, ready to be used. And then what you also get an advantage is the libraries, the code infrastructure are all in one place, and they also provide a good APIs for you to perform those analysis without downloading any data sets to your local machine. And then you can use the power of the Google computation clusters for running the task. And then various kind of data sets from Landsat to Sentinel to models to various kind of data products are already populated and available into the system. Now think in terms of the data locality, because now your code is running in the same location where the data is. Otherwise you need to first download the data, bring it into a system before you can do it the processing. And remember that, as I said, IU cost is always more than the CPU processing cost. So if the data and the algorithm resides on the same location, then the processing could be done very fast. Another thing is that Google Earth Engine provides it provides both the JavaScript based API as well as the Python based API. So people can directly code using these code editors, and also it provides good documentations are also available, even sample scripts are also available. The good thing is various algorithms are related to performing this big data analytics are already built in. The scripts that you write could be shared across among people. You can visualize the result in the same place. There's also a provision of saving the script, running the script, coming back later, and then performing those operations. So this Google Earth Engine is a good cloud-based environment wherein the user need not to worry about the data downloading, pre-processing, that is being taken care of, and also the he can spend more time in what has to be done, more on the getting the insight or analysis than working on those pre-processing chain, which also takes a lot of time. Just to give a glimpse of the power of this Google Cloud infrastructure, so this is an example of the very popular example of Google Earth Engine, which is a time-lapse animation. As you can see, if you want to do a assessment of the, let's say, the glacier retreat over a period of decades and over multiple years, then you can see that how much data you need to analyze. And coming to your traditional way, so all those data has to be downloaded, the radiometry, geometry correction, pre-processing before you can do any such kind of analysis. But here all the data sets are readily ingested and available, and then you can perform various kinds of studies, which could be glacier retreat, seeing how the deforestations are happening or how the urban growths are carrying on. So using this cloud platform and this big data helps it in a tremendous way. So in this introductory lecture, we talk about the overview of the big data, and we see the various aspects, how we characterize a big data primarily from the various V's. We also talked about the types of big data types, like structured, semi-structured, and the unstructured. We also have seen the typical analytical workflow that is involved in the big data analytics, and followed by this discussion on the two popular frameworks, which is Hadoop and Spark, followed by some specific spatially enabled frameworks that we have discussed, and finally I've also discussed on the how does the cloud computing maybe is beneficial for this big data processing. Thank you, and then